Hey everyone, welcome to this multivariable calculus course, and in this we are going to cover all the topics and subtopics, problems, practice problems, previous year questions, and everything we will discuss in this course. Okay, so let me tell you about this course, how we are going to proceed in this. First one is in this multivariable calculus we have the following six topics, and most of the students feel difficulty in these three. Okay, so I'll explain all these in detail. The first one is three-dimensional space, then partial derivatives, applications of partial derivatives, multiple integrals, line integrals, and surface integrals. Today I'm going to start with this three-dimensional space, and I will discuss the introduction to three-dimensional space or the 3D coordinate system today. How things behaves in 2D, 3D. Okay, what is the extension? How can we generalize it? Okay, so we will discuss all these. It is the basic unit, you can say, for our multivariable calculus. Okay, so let's get started with the introduction to 3D coordinate system today. So for 3D coordinate system, as you are already familiar with the two-dimensional system, right? You have two axes, x-axis and y-axis, which are perpendicular to each other, right? And you can write the numbering 1, 2, 3 positives on this side on x, and this is y. So here you have -1, -2, -3 on the along the negative x. These two axes, x-axis and y-axis, are perpendicular to each other. Similarly, you can write the numbers on 1, 2, 3 on y-axis, and on the other side it is -1, -2, -3, and so on. Okay. So basically, we have this Cartesian plane over here. It is your two-dimensional system, right? For two-dimensional system, we have these x-axis, y-axis, which divides the plane in four parts, right? We call them quadrant. This is your first quadrant, and we always move in anti-clockwise direction because anti-clockwise direction is considered as the positive direction actually. Okay, so this is first, this is second, this is third, and fourth quadrant, right? So we get quadrants in this. Okay, if there is a point lying in any of these quadrant, okay, so that will have two coordinates. P is any point, okay, having its coordinates as, let's say, x and y. So here what is x? X is the distance traveled along x direction, and y is distance traveled along y direction, right? So this distance is actually x, and this height over here is actually y, right? Okay, so now let's generalize this idea to the 3D. So in three-dimensional space, not only two, we will have three axes which are perpendicular to each other. That makes a space, as you can see here, with the x-axis and y-axis. This will make a plane, but we have another height part as well, z-axis. Okay, so height is there, which requires another coordinate, right? So we need a new axis, which is z-axis over here. So in this way, we have a point having its coordinates. Then what will be the coordinate? You will be having its x coordinate, y coordinate, and z coordinate, right? So I will have here, I can write it as any point over here, P, will be having x, y, and z. Okay. Now, x is again distance traveled along x direction. Okay. Y is the distance traveled along y direction, and z is the height part. Okay. So here this is z part. So in this way, you can mark the coordinates of the point, but this time it will not make quadrant. It will be, there will be octants, 8, right? 8 rooms, you can say. Okay. Here we have this x and y axis. So the plane formed by this is the xy plane that we have already studied in 2D. This is the same xy plane over here. So we also call it xy plane, and we can also call it z equals to 0, because on this all the values of z are 0. So z equals to 0 is the equation of this xy plane. Remember this. Now if you consider another plane, okay, on here, which is parallel to our xy plane. Let's say this plane is parallel to xy plane, and here the coordinate of z will be same throughout the plane. So let's say it is having the x coordinate and anything, y coordinate can be anything, but z coordinate as 5, let's say. So the equation of this plane will be z equals to 5, because on this plane, right, on this plane, the z value is always equals to 5. Okay. Now, next part. So in this way, as I was saying, we can extend this x to the other side, which is negative x, and similarly for y, we will have negative y values. Similarly for z axis, we have negative z values also, right? And this gives rise to octants. There will be 8 such octants or rooms, as you can see here. Okay. Now, first, second, third, fourth octants also calculated in the same anti-clockwise direction. Okay, so if this one where x, y and z all are positive is the first octant. Now if you move left in the anti-clockwise direction, right, so you will reach to another side having the x value is what? Negative on that side, but y and z are positive. So in the first octant x, y, z all are positive. In the second octant, x is negative, y is positive, z is positive, right? So you will have 1, 2, 3, 4, 4 octant on top. Similarly, 4 on the bottom, just below to this xy plane. So total 8. So that's why we call them octant. Now, the formula for the distances. If you have 2 points lying in the 2D, so let's say P1 is the point having its coordinates say x1, y1, and Q, so or P1, P2, let's say, another point having its coordinates x2, y2. So if I join these two, I know the distance between them is given by this formula, square root of x2 minus x1 whole squared plus y2 minus y1 whole squared. Okay. Similarly, if I generalize the same thing for the 3D, I need 2 points in this space. So let's say P1 is having its coordinates as x1, y1, z1, and P2 is another point having the coordinates as x2, y2, and z2. Okay, so for that, one second, P is point having its P2, x2, y2, and z2. Now, in this way, we can have the distance between these points as what? Square root of x2 minus x1 whole squared plus y2 minus y1 whole squared plus z2 minus z1 whole squared. What I'm doing actually, I'm just generalizing the thing from 2D to 3D, as you can see. Okay, so you can generalize it from 2D to 3D like this. That's it. So in this way, we can find the distance between points in 3D as well. Okay. Now, next part. Let's solve some questions. As I said, the 8 octants are there and their respective signs are already mentioned over here. Let's solve some questions. First part says, find the coordinates of the projection of the point 4, -3 and 7. So there is a point, which one? 4, -3 and 7. So it lies in this octant, as you can see here. What is it? It is 1, 2, 3, 4, fourth octant, right? So there is a point lying in the fourth octant. Now it says find the projection of this point on xy plane. So let's say there is a point over here. This is the point. It is 4, -3 and 7. Now if I drop a perpendicular from this point on xy plane, ground, right? So ground. What will be the coordinates of that point? So obviously on the ground level, z value is 0. That will not affect distances traveled along x direction and y directions, right? So basically the plane, xy plane, or we can also call it z equal to 0, on that we will be having the coordinates of that projection will be as 4, -3 and 0, simple. Okay, so in this way you can find it. Next one, xz plane. So now I have to drop a perpendicular on x and z. So which one is xz? This vertical one. So on the vertical one, xz, the value of y is always 0. So put y equal to 0. So that gives 4. We are not traveling any distance along y direction this time. Okay. So we have what? In this 4, then it is 0 and the z coordinate as 7. This is your y equal to 0 plane. Okay. Or you can also call it xz plane. So on this xz plane, we are not traveling any y distances. Okay. We are not going left or right. Simple. Okay. Now, next part is z-axis. Now, if I drop a perpendicular from the same point over here, let's call it P, on z-axis. So, on z-axis, what do we have? Here, this is z-axis over here. So, on z-axis, we are not traveling any distance along x or y. We are just moving up by what? 4 units. Okay, so for this case, you will be having 0, 0, 4. Okay, answer. Okay, now let's move to the next problem. You can take a picture of this, and if any of you have anything to ask, please feel free to ask in the comment box. And you can also contact us using this WhatsApp number, okay, anytime for any one-on-one classes, regular courses, or you can have the details by contacting us. So, next part. We have to draw the graphs of x equals to 3 in r, r squared and r cubed. What that means? R means in one dimension. Okay, so we will be having only one direction, 1D. R2 is for the plane. We have two axes, x and y. R3 is your space, 3 axes. Okay, so now we have to draw the graphs and we will check what that represents in R, x equals to 3, what that means in real numbers, in plane or in space. Okay, let's do it one by one. We are going to generalize the things. Basically, for example, in 1D, you can consider a point. Its 2D part is what? Having some length and breadth basically. Two axes are there. So circle you can consider. Circle in a plane is what? Is 2D figure, right? 3D. For 3D, sphere. Okay, sphere is the generalization for that circle because you have height as well. Okay, cylinder, cone, like this. Okay. Now, let's draw the graph for x equals to 3 in R. So, we have only one axis this time. So, let's draw only one line and you can mark the point 0, 1, 2, 3 on the right side and -1, -2, -3 on the other side. So, let's write it directly. This is the line and plot the points. Now, we have to mark x equals to 3. So, just go to x equals to 3 over here and this is your answer. That's it. It is just a dot. Okay, it is in 1D. So just a dot. This is the graph for x equals to 3 in real line. Next is for r squared. So we need Cartesian plane, x-axis and y-axis. X equals to 3. It means, what about y? Y can be any real number. So you are already familiar with this, right? You just have to go to x equals to 3 and draw a line because y can be anything. So this is the line x equals to 3 over here. Y value can be anything on this, but x value is always 3. So this line represents x equals to 3 in plane. Right? Now, we have to generalize this to R3 in the space. How can I generalize it? See, let's start with this 1D to do 2D part. I started with 1D and I got only one point over here. Then for 2D, I generalized it because y can be any real number. So that's why I said all the y values, right, lying here will be a part of the solution. Now, if I have to generalize it for the third axis as well, so what will happen in that case? In that case, you will have a combination of these lines, right, which will make a plane, entire plane. Okay, where x is always 3 and y and z can be any real number. Z-axis is also there, so you can cover any height, you can cover any breadth, but keeping this length same, which is x equals to 3. I'll show you on Desmos also, one second. Here, if I have say x equals to 3, so what is that? In two-dimension system, it is just a line, right? In 2D, it is just a line, but for 2D. Now, if I generalize the same thing for 3D, what is that? It is a plane. See, it is a plane over here having x equals to 3. X value is 3 over here. Okay, this is your plane. Yz can be any real number, but on every point on this, the x value is only 3. As you can see, we are only traveling 3 unit distance on x, but no restriction on values of y and z. Okay, so we got this plane in this case. Okay, that was about the x equals to 3 only. Okay, so we got a plane in this case on traveling 3 unit distance along x direction, right? One more question. This was in one value, right? One variable was given x only. So let's consider another example where we have both x and y. And we have to draw the graphs for this on plane as well as in space. So for y equal to 2x minus 3, you are already familiar with this thing in plane, right? That represents a straight line, right? Having the gradient as 2, it is a straight line having gradient equals to 2, and what is the y-intercept? Y-intercept is negative 3 because I'm just comparing this y equals to 2x minus 3 with y equals mx plus c, where m is the gradient and c is the y-intercept. So that straight line will cut the y-axis at 0 comma minus 3. Okay, so our line will pass through 0 comma minus 3 and will have the gradient as 2. So you are already familiar with this, so I'll just directly draw the graph for y equal to 2x minus 3 in plane, and I'll generalize that in 3D because again here that line is okay, but there is no restriction on z value. So what you will get? You will get a plane, okay, where that will be true for any value of z. So in 2D, as I said, there is a point what x, if you put x equals to 0 here, you will get y as minus 3. So this is the point over here, and similarly if you put y equal to 0, you will get x as 1.5 over here. So just join these 2 points and this is your answer. This is your graph for y equals to 2x minus 3 in plane. Now if I have to generalize it, okay, what can I do? Again, I will consider the same plane. Okay, I can take those same. I'll get the similar line. Don't worry about that. The line will be similar to this one only. So you will have say this one and minus 3 over there. That is the line. Okay, this is the line that we have. Now there is no restriction on z direction. So this is going to be a plane. Okay, it is going to be a plane, but this time it is oblique. It is not parallel to xy plane, yz plane or zx plane this time. Okay, now let me show you on Desmos. Over here, let's say we have another equation y equals 2x minus 3, right? In 2D it is a straight line, right? And in 3D, what is that? Generalize that, so you will get a plane. This time it is not parallel to any of the xy or yz or zx planes. Okay, but yes, there was a line y equal to 2x minus 3 and just take any height. So you will get this plane as you can see over here. Okay, now let's get back to the same question. So we will get this plane over here. Now let's generalize it to not only the linear equations but any equation. Okay. For example, we have x squared plus y squared is equal to 4. So x squared plus y squared equal to 4 in r square. What that represents? What is that? It is a circle with center at origin and radius as what? 2 units. Why? Because equation of the circle is given by x minus a whole squared plus y minus b whole squared is equals to r squared, where this a comma b will be the center. So in this case we have 0 0 and r will be the radius. Okay, so here I have 4 which is 2 squared. I can write this 4 as 2 squared. So 2 squared 4 answer. Radius is 2 units overall. So in order to draw this thing in 2D, okay, first I will take these xy axis and draw a circle of radius 2 unit and passing through these 2 points and having the center at origin. So yes, I can simply draw a circle like this. Okay, like this. Now generalize it to 3D. So in 3D, I need my z-axis also. So let's consider this. So what I have actually, I have a circle in 2D. So I'll draw a simple circle in this way. Okay, over here I can draw a circle, but I have to generalize it in 3D. So I will get more and more circles along this same height. Now if I combine all these, if I combine all these, what I will get? The radius is same for all of these. Okay, the radiuses are not different. So radius is same for all these. And if you join all of these, you will get a cylinder at the end. Yes, that's the answer. Cylinder. That represents a cylinder in space. So this thing represents cylinder in space and circle in 2D. Right over here, it was circle earlier. Now, as now we have seen, it was representing over here r square. It was a line, but for space, it was a plane. So that is it. And hence that was the introduction to the 3D coordinate system. So in this session I explained how to generalize that distance formula from 1D to 2D to 3D, then how to draw the graphs. Okay, so you have to consider that 2D shape first and generalize it to 3D. Okay, later we will discuss some quadric surfaces. Okay, you will see those here, and you have to memorize few results. Okay, like ellipsoid, paraboloid, hyperparaboloid. Okay, and hyperboloid of one sheet, two sheets, and so on. So that we will discuss in detail. Don't worry about that, but I just gave you an introduction to 3D, and I will generalize the same thing to cover all the other topics. So in the next session I will discuss the equation of lines, okay, in 3D, its vector form, its Cartesian form. Okay, I will discuss this one in the next one. So that is it for today. Thank you for watching this session. See you in the next part. Keep watching, keep learning.